Welcome to Silicon Talks from Electronic Praxis, where we look at the tech that goes into your tech. I'm your host, Stuart Cording. Electrical energy is at the core of most of our lives, powering our homes, industries and transportation. For decades, we've relied on fossil fuels and nuclear power, but more recently there's been a transition to renewables like solar and wind. Of course, these sources aren't always there when you need them. To solve this, the electrical grid is increasingly installing battery storage solutions, termed BSS, to store excess energy when it's created and return it to the grid when needed. And this is a significant application. According to PwC, there is around 36 gigawatt hours of BSS capacity installed in Europe alone. So what goes into building a BSS? What standards need to be adhered to? And how do we ensure that those lithium-ion batteries are operated safely? To help us with these questions today, I'm speaking to Marcelo Marques, Global Marketing Manager, Power and Energy from NXP. And if you're watching live, don't forget that you can participate by sending us your questions, and we'll try to answer them by the end of the show. So, hello and welcome to the show. Great to have you here, Marcelo.
Thanks, Stuart. Thanks for having me.
So let's get kicked off with our first question, and it's fundamental to the topic for today. What is a battery storage solution? What does it do, and where are they being deployed?
Okay, good question. Well, I have three questions here, right? So first one, what is a BSS? So as you said, it's a battery storage system. And this is electrical energy by converting the electricity into chemical and energy within battery cells. Okay, so this energy can later be released when you need it. This process has a lot of electrical chemical properties, and it's very interesting to know that there are many types of battery chemistries out there, and they vary in density, efficiency, lifespan, and safety. So that answers the what is a BSS. Now, what does it do? So it has multiple applications, many use cases. So the first one is energy storage. So you have electricity generated from renewables, for example, like you mentioned, solar or wind. So this type of sources, they don't provide energy constantly. So you need some sort of way to store that energy, and then you use whenever it's needed. There is also use for grid stabilization. So, for example, it helps to balance the frequency and the voltage of the grid, because there are multiple fluctuations. So the energy storage system will be acting like for the electronic engineers out there, it's like a big capacitor. Also, it's used for peak shaving or arbitrage. So, for example, when you have the electricity cost fluctuates and goes high, you can then use a battery storage system. And when the electricity cost is low, you can then buy from the grid and store that energy. Can be used as a backup power, for example. You can integrate, like I said, with renewable energies. One interesting use case is for solar panels, for example. We have solar farms, and those solar farms, they don't have the power inertia to keep the frequency of the grid stable. So, let's say if the sun, there's a cloudy situation, and the panels are not generating enough power, you need those storage systems to push that energy back to the grid to maintain the frequency. We've also seen some electric vehicle charging support as well. So imagine you're in the middle of the road, there is no electricity, but you need to charge your car. The only way to solve the problem is that you have the solar panels or some sort of renewable energy source, and then you need the the battery storage system to provide the energy for the EV chargers. Okay.
Yeah, so sounds like a good overview.
It is. And where is deployed? So again, that's the third question, and we have a few applications here. So one is residential. Homeowners, they use solar panels on their houses. They want to store that energy. That's one of the applications. The other one is commercial and industrial. So you have, factories or buildings. They want to have some sort of energy storage. That's another application. Utility scale. So you have this huge containers of batteries, deployed, connected to the grid. That helps to stabilize and give some reliability to that grid, and again integrate with renewable energies. Mobile robotics and off-road vehicles. That's an interesting one.
Yeah.
Mobile robotics, they need high voltage batteries, right? And like I said, EV charging infrastructure, and then the data centers. That's a new one that we've been hearing a lot, especially with AI. You have a lot of fluctuation inside data centers, and sometimes they need some energy storage to maintain some stability on the power for those data centers.
And so what sort of voltages are we talking about inside the battery system itself, and how are they sort of constructed?
Yeah, so the voltages, they vary a lot, right? So you have voltages ranging from, residential, low voltage below 60 volts. Sometimes they can go up to 400 volts. But on these large storage systems, we see up to 1500 volts. So it varies on the application. It varies on the chemistry of the battery you're using. So that's why you need sometimes when you creating a system for all these use cases, you need to have a very flexible and modular platform so you can
Yeah.
scale the voltage and the current.
Yeah. And I think I guess that's important for a manufacturer and a supplier of BSSs. They want to be able to learn and develop their technology, but then apply it to lots of these different applications, and need that sort of scalability behind it.
Correct.
So then, if we were to, we've heard a lot there about the applications, where they're used, and got some of the sort of general requirements in terms of the voltage, and also that need for some sort of flexibility in the architecture. If we were to take a look at a block diagram of a BSS, what would we actually see as the key blocks there?
So if you look at the energy storage system, there are multiple pieces and components on this storage system. I have a slide here, I think I want to share. Let's see. Okay, let's move to this slide here. This one is showing a container for a storage system. And as you can see here, there are three main block diagrams. One of them is the cell management unit. So let's go a step back here. If you have one of these containers, you're going to find a lot of racks inside. And each one of these racks will have some in this block diagram. Inside each one of the racks, you have a cell management unit, the high voltage box or battery junction box, and you have the battery management system. So each one of them have specific functions. The cell management unit is measuring the voltage, the temperature of the cells, and it's directly connected to the battery cells. You have the high voltage box or the battery junction box measuring the current for the storage system. And then you have the battery management unit, which is managing the entire system and taking care of all the functional safety features that are necessary to maintain the system working in a safe and reliable way. Okay.
Looks good. Yeah.
And this is in the rack, right? But if you look outside of the rack, you also need to have the power conversion. So you have the DC to AC power stage that will then connect this storage system to the grid. And you have some energy management controlling as well, because you need to control when you deploy the energy, when you charge the battery system, and how you do the cloud connectivity and data acquisition for data analysis of this.
So there we've got quite a few different types of technologies, quite a few different things that need to be resolved when we're designing these things. And I think one of the sort of key concerns that somebody might have looking at these, maybe one of the issues that could arise, is with the battery storage. Obviously, lithium-ion batteries, I think everybody's used to the fact that they can be a fire risk. We've seen that in some of those electric scooters, for example, and also in electric vehicles. And mishandling them can also cause them to catch fire, or they can also degrade with time. And there's all those high voltages and currents, and you're then taking this container and you're connecting it to the electrical grid. I'm assuming that there's quite a few different types of standards which are relevant to the design of a battery storage system.
Yes, Yes, you're correct. So batteries are dangerous, if you don't use them correctly. But if you use them correctly, they're pretty safe. Like if you compare that to combustion engines, for example, on vehicles, it's more likely that a combustion engine will catch on fire than an EV, for example. So yeah, so for handling all this and the battery storage system, they have to comply. They must comply with some electrical and functional safety regulations. And the two main ones are the IC 61508 and IC 60730. So IC 61508 is a functional safety for electrical and electronic systems that is applicable for BSS. And the IC 60730 is for fire and thermal protection standards. I also have a slide here that shows some of the standards. So let me go back here. And if you see on this orange portion, it's listing all the functional safety standards. Okay, and that's what NXP is offering. I'm going to get into some of that details later. But for your product, so when you deploy the final product, which is the entire battery system, you need to comply either with the IC 62933, IC 62619, UL 1973, and UL 9540. So all these regulations, all these standards, they uh, they will look into all the safety features in your system to make sure that your system is safe and reliable.
And for those who are maybe new to this type of application, I mean, those are standards which are relevant for other types of applications, which are also grid tied, I assume, or work with dangerous materials or chemicals like a lithium-ion battery. Is that the case?
Yeah, that is the case. Yes.
So we have a very complicated system. There's lots of safety relevant concerns, and there's plenty of standards that need to be fulfilled. You're part of the NXP team that focuses on this type of application. What are you doing to help customers who want to engage in this space, to sort of give them a helping hand and get them to a functional solution as quickly as possible?
Uh, so what NXP is doing to help our customers is providing them a complete reference design. So I don't know if you can see this slide on a big screen because okay, there you go. So this is what we're offering. So this reference design is for high voltage energy storage. And what NXP is doing is providing three main components for customers that want to design their own BMS. So the first component is the hardware piece. So we give our customers all the hardware schematics, the PCB layout, the Gerber files if they want to just copy this design. Um, and it's the BOM, we don't hide anything, like all the hardware is open to our customers. We also provide the software piece, which is the blue portion on top. We give all the layers of software for our customers, so from the low level drivers all the way up to the safety application manager, to the data handler. There are a few things customers they need to implement themselves, state of charge and state of health, for example, because that is a chemistry dependent, and it's system dependent as well. The topology, depending on the voltage that they use, they need to make some tweaks on the software. And then we certify the system, so we provide the functional safety certification. So this is IC 61508 and IC 60730 compliant, so it has U2 and class B certification.
So with that, then we've got, like you said, you've got the hardware. Each of those building blocks is there in terms of hardware, with a bill of materials and a reference design. We've got as much software as can be independent of other factors like battery selection, battery chemistry, and other bits and pieces, and then all the safety elements of that.
Yes.
If we drill down then into the software element, do you, at that point, are you just providing sort of the drivers for the processor and some of the off-chip peripherals which are included in this design, or is it a little bit more than that?
It's a little bit more, and it's not only the software, which is the important piece of this reference design. It's a combination of software and hardware, right? So when you're making the systems, they need to be modular, they need to be flexible, and our system is good for up to 1500 volts, 500 amps. The software component is divided in two pieces. So we have actually our MCU inside this reference design is a dual core MCU with one of the cores in lockstep. So the safety portion of the software runs on this lockstep device. And then we have all the other application portion or the quality manager core running the application that is gonna that our customers can customize and modify.
And is that based on a particular operating system as well, or is it operating system agnostic?
So on the quality manager portion, so on the application side of things, it runs on top of a FreeRTOS, so it's a real-time operating system. And on the lockstep core for the safety management piece of the software, it is a bare metal.
And then maybe for those who've not sort of explored that sort of type of processor before, what is a lockstep core, and how is it different from a standard microcontroller core?
So the main difference, in a nutshell, you have two identical cores, and they're running the same application, and they have to agree on the answer simultaneously for the system to move forward. If not, then the system is put on a safety state. It means there's something going wrong with the microcontroller, or something going wrong with one of the cores. It could be even like an SU event, single event upset, for example, which is a alpha particle or a beta particle coming from outer space or from some radioactive material nearby and hitting one of the transistors and flipping a bit. So, that's one of the reasons why I use a safety core.
So we've started then on this journey now into the area of functional safety. It's also sometimes abbreviated to FUSA, I think. How much of that depends on the hardware you've recommended, and how much of it is sort of leans upon the software, and how much more do your customers need to do with the software that you provide them with?
That's a good question. So it's a combination of both. So functional safety is looking at all the hardware components, how you design your PCB, even like the distance between the traces, all the component qualifications, and they also look at the software. So one example is, for example, when you're measuring the temperature of the battery cell, you have a temperature sensor that is connected to a microcontroller, and that is the hardware portion. So functional safety will look into all the aspects of that temperature sensor, if there is redundancy, if it's connected properly, etc. And then the software needs to look into that data coming from that temperature sensor, make sure the data is correct, make sure that they are making the conversions correctly, and then triggering some functional safety features in case of over temperature event on the battery cell. Yeah. NXP is providing, the IC 61508 and 60730 for the BMS. But once our customers, they design their own storage system, they can use this functional safety certification from NXP, but they also need to add some other aspects of functional safety for their system. So there's cooling, and there's some other things on the container that is not part of the BMS that our customers they have to do. But I would say 50 to 70% of the work on functional safety is already done.
I mean, what's that in terms of sort of hours of work that needs to be done typically if you didn't have that prepared for you?
So if a customer does not have a lot of experience with functional safety certification, they can save up to a year of work. But we claim, I think it was like 40 weeks or something like it, that they can save if they are starting from scratch, because you have to work on the structure of the functional safety documentation, and you have to go over each one of these documents and make sure everything is complying with the standards.
Yeah, exactly. Yeah, I work a little bit more closely with the automotive industry and realise how much effort needs to be undertaken there to fulfil safety, functional safety requirements. And it's really. I personally have the feeling that it's almost a science of its own, and people can dedicate their entire careers to fulfilling all these things and keeping on top of them. So I've read a few standards in my time, and they're not particularly interesting. So how they stay awake, I'm not quite sure.
Yeah, I know. you need dedicated engineers for functional safety. You need a full-time engineer just working on functional safety, especially for energy storage. It's not fun. It's a lot of work, and there's a lot of iterations as well, right? You have to submit your documents, they come back, and then you submit it again, and then you rewrite. So it's boring in a way. And no one likes doing that. So that's one of the reasons why we're helping our customers. The energy storage system is a new technology, right? It's been around for a while, but now it's growing like 30% year over year. So there's a lot of companies that want to get into this market, and they want to get quick. So by using our reference design, I think it's the shortest path to market.
Yeah.
And the easiest one.
One of the other things I was going to highlight with you, I was talking to a few people at trade shows last year, Embedded World and Electronica, and I've heard that there's something called a battery passport at EU level, which is sort of in discussion. And the idea of it is to sort of enable batteries that have been used in different applications, like a car, for example, to have a second life in an application in a battery storage system. Do you have any more sort of information on that? And is that passport capability something that needs to be considered in a reference design like this?
Yes, especially if you're selling in Europe, because battery passport is going to be required by the European Union. And battery passport, if I explain very quickly, it's a way of storing some static and some dynamic data from the battery. So on the static portion of it, you have to give it a unique identifier. You have to provide all the battery manufacturer information, the chemistry, etc., where it came from, the model, the type, the density, the capacity, etc. And on the dynamic portion, you want to know what's the state of health, the state of charge history. You want to know the cycle count and the depth of discharge of that battery. If that battery went through any temperature or safety events. So all this information needs to be stored in a very safe manner, because you don't want anyone to modify the data. Right? The intent of battery passport is when you give a second life, you have all the history of that particular energy storage system.
And I was going to ask, is the intention there as well to make sure that information's available for every cell in a pack, or is it more, is there some sort of standardized pack number of cells in a pack?
It's for the pack, so it's not for the cell itself, because there is no way you can track that particular cell, but there is a way you can track the modules inside the battery pack or the entire pack itself. Our platform actually is battery passport ready, so we have a secure element on our BMU, and we are providing now all the software layers for the battery passport, so it complies with all the standard. And we also offer a very secure way for cloud communication, because one of the things you can do with battery passport is also move that data over to the cloud, and then you could have, for example, an NFC tag on your battery pack. You scan it, it connects to the cloud, and then it provides you all the data for the battery passport.
Wow. Okay. So I think we're going to see a lot of changes. There's also so much other EU legislation going on at the minute in terms of sustainability and sort of recycling of electronics and designing to be recycled and reused. So it's an interesting time, I think, for the electronics industry generally, and the legislation I've seen as well is making sure that companies outside of Europe also have to apply those rules as well. Yeah. So
it's interesting you mentioned about recycling, because one of the things you have to store on the battery passport is how to recycle the battery.
Oh, really? Okay.
Yes. Yeah. You have to put all the materials and some guidance of how to recycle that battery.
Yeah. Okay. Interesting. Well, we're running quickly towards the end of our time here. It's been really fascinating to sort of get all that collection of information and right from the application end right down into the details of how it's actually implemented as well. We're just going to take some Q&A questions, which I've got some here now. It's just one of the topics that sort of come up is around sort of new so active cell balancing, for example, and how How is the cell balancing within those battery packs being handled today? And are you seeing new methods for that, or more improved methods for doing cell balancing?
Yes, that is a really good question. Comes up every time. So thank you for that. There are two ways you can do balancing, right? So you can do with passive resistors, or you can do actively. Uh, you need balancing. Just give a background, because the chemistry and the batteries will vary between each other. So not every cell is going to be identical to another cell. And when you're charging and discharging, you're going to have a difference in state of charge and voltage on the cells. So one of the things you need to do is make sure that all the cells have the same state of charge, same voltage, and you need to do the balancing. With active balancing, the idea is you move that energy between, the pack to cell, or from the cell to the pack, or in between cells. I am working right now, so we have a team at NXP that are about to release an active balancing solution. But our reference design, as it is right now, the 1.0, is using passive balancing. The advantage of the active balancing is you increase the availability of your system, because you can, I like to say, with the passive balancing, your capacity is as good as your weakest cell.
Right.
And with active balancing, your capacity is as good as your strongest cell, because you can always top up the weak cells to match the
Right.
state of charge of the good cells. And also you extend the longevity of your battery storage system, because imagine if your system is good up to 70% state of health. Whenever your weak cell reaches that stage, your system is done, right? It's end of life. But if you have active cell balancing, you can actually prevent that weak cell from aging by constantly moving some current through that cell, so that cell doesn't discharge as much as the other cells. So you're
Right.
actually saving a little bit of the lifetime of that cell, and therefore your entire system life extends by a few years, actually. So
Wow.
it's a very interesting technology.
Yeah, that's one of the things that fascinates me about the electronics and semiconductor industry in all the years that I've been involved in it, is that there's always somebody sitting there tweaking and improving some tiny, tiny little functionality somewhere in something, which will have a really big impact, in this case, on sort of like the longevity of the cells and how long they're useful for. I think it's just absolutely fascinating.
Yeah.
Another area, I was doing a bit of research, obviously, before we sat down to talk with one another. And one of the things that came up was, if we imagine that the BSS that we looked at is essentially a DC battery, there's a discussion around an alternative topology, which would be what they call an AC battery. Do you know anything about that at all?
Yes, I do. So the idea of the AC battery, or there are no AC batteries, all the batteries are DC, right? But the idea is, when you stack those batteries in series, each one of those battery cells has a tiny little voltage of, between, let's say, 2.8 volts to 4 volts, and you could recreate the senoid, the 60 hertz senoid, at 181 volts peak, or 110 volts RMS, by switching these batteries in and out of the chain. So imagine if you could select each one of the batteries to get into the grid individually, and you could modulate, or if you PWM these batteries,
Yeah.
you could then recreate the senoid at 60 hertz, and therefore you don't need the power conversion stage. So you eliminate the DC to AC conversion that we typically use on these storage systems.
Yeah. I guess that also would lead to an even higher efficiency as well if we're getting rid of a power stage.
It reduces the weight for sure, right? So, for example, for portable devices, that is something like portable
Yeah.
batteries. That's something we've seen a lot of application.
Yeah.
It helps with the efficiency, but also helps a lot with how you manage the battery. So, for example, active balancing comes for free when you have this switchable or AC batteries, because if you have a weak cell, you just put that on the top of the senoid. So you
Yeah.
utilizing for less time than all the other batteries. So
Yeah,
there are
exactly.
many advantages, but that comes with a very complex system, right?
Yeah.
How you manage the software to control all this, right? It's not so easy.
Yeah, but as you and I know, the electronics industry makes these complex systems simpler and integrates them into another chip. So I'm sure they'll come up with a
Yes.
way to make it simple at some point.
Yeah. Correct.
Fantastic, Marcelo. Well, it's been lovely to talk to you. Thanks you ever so much for taking us through battery storage systems and all the elements that go around that. Where can people meet you if they want to come and talk to you in person, maybe at a trade show if they're around in the next few months?
Yeah. So the next one, I'm gonna be at the Smarter E in Munich. That's on the first week of May. So
Yeah.
NXP will have a booth there, and we're gonna be displaying our latest technologies on the energy storage. So you're welcome to show up.
Yeah, super. Well, thanks
Okay.
ever so much. It's been great having you.
Thank you so much for having me.
Well, that's all we have time for in this episode. So, what have we discovered? Electrical grid operators already have systems to perform peak shaving and stabilise the grid. BSS is an alternative to these that is more eco-friendly and complements renewable energy sources like solar and wind. However, leveraging the storage capabilities of lithium-ion batteries and operating at high voltages and currents, these systems are subject to a broad range of safety standards. Semiconductor vendors like NXP have a great overview of the complete system and provide devices from sensors to microprocessors, all with software in a reference design. Having already tackled many of the functional safety challenges, BSS design teams only need to add their application-specific capabilities and finalise parts of the safety requirements. My thanks go to Marcelo Marques from NXP for his insights into BSS technology. Thanks for joining and participating in today's show, and if you're looking for more deep tech stories, don't forget to drop by the Electronic Praxis website.